Yeah, well, the research in the Koch Institute is broad. It's basic in orientation, but increasingly has direct connections to problems in clinical management of cancer. And there are a number of areas that we specifically focus on. Nanotechnology is a good example. We have many chemical engineers and material scientists who are interested in developing new materials for delivering drugs, either conventional cancer drugs or experimental cancer drugs, specifically to cancer cells. And nanotechnology allows one to do that by targeting these materials directly to the cancer cell. The materials are embedded with the anti-cancer drug. And in this way, the drug gets brought to the cancer cell, delivers its payload to the cancer cell, and avoids causing damage to normal cells. So we, on the one hand, get better efficacy, and on the other hand, have reduced toxicity. So I call these smart bombs for cancer, and nanotechnology is a wonderful way to achieve that. So many of our investigators are involved in nanotechnology applications. A second area is building new devices for monitoring cancer and detecting cancer at earlier and earlier stages. On the one hand, we want to improve diagnosis. If we could find cancers at earlier stages of their disease course, our ability to treat patients would be greatly enhanced. Part of the problem with cancer treatment today is the disease is not diagnosed until the patient has disseminated metastatic disease. The cancer cells are throughout the body, and they're very difficult to control at that point. If the cancer is localized, it's often resectable by surgery, and the patient can be cured. So we need to shift the curve of diagnosis to earlier and earlier stages, and several of our investigators are working on technologies to allow us to do that. Another example within this category are devices to monitor the state of an individual's cancer in real time. For example, implantable devices that can be placed in the body and can continuously measure the presence of some cancer-associated biomarker. In that way, you could know whether the disease is in remission or starting to reemerge in the form of relapse. And the sooner you know that, the more quickly one can take action and hopefully control the disease more effectively. So implantable sensors for cancer is another emerging area within our labs. A third category is metastasis. I mentioned that metastasis is a deadly phase of cancer. In fact, 90% of cancer deaths are due to the metastatic phase of the disease, and yet it's a phase we don't understand nearly as well as we need to. So we need to, on the one hand, figure out the biology of metastasis. How do cells spread? How do they survive and thrive in distant site? What does the local microenvironment of a metastatic tumor look like, and how might we be able to treat those cancer cells at that distant site? We also need new technologies to find those metastatic cells in very small quantities so we can figure out what they're doing and see whether we can control them. A fourth category is in the area of personalized or individualized cancer medicine. And this really is a follow-on to the era of cancer research that precedes the Koch Institute, the era that's represented by the MIT Center for Cancer Research, where we've sort of laid out a roadmap of how cancer emerges at the genetic level. We're not finished with that process, but we've made tremendous progress. And we now believe, based on that information, we can design much more specific, much more effective therapies. And we have examples of that, like Gleevec and Herceptin. But we need more. And so we're working actively to figure out new treatments based on the genetic alterations in cancer cells. And related to that, we're trying to figure out how cancer cells become resistant to the therapies that we do have. These new age drugs, like Gleevec and Herceptin, are remarkably good, but all too often they fail. And when they fail, it's because the cancer cell has figured out an end run around the drug treatment. They become resistant. We need to understand the molecular basis of that resistance so that we can figure out new therapies that avoid resistance or therapies that, when added to the original drug, overcome that resistance. And that's an active area as well. And the fifth category, and the final one, is cancer immunology and immunoengineering. And this is important because, in theory, your immune system is a tremendous ally in the fight against cancer. because the immune system is designed to detect differences between your cells and things that invade you. Cancer cells acquire differences as they develop, differences that should be detectable by the immune system. However, given the fact that people do develop cancer, it's clear that the immune system fails us. And in fact, the cancer overcomes the immune system. It suppresses the activity of the immune system, allowing it to grow and eventually kill the host. We need to understand the mechanisms by which the tumor suppresses the immune system and arm the immune system to fight back. And we're figuring out ways of doing that. Developing, for example, new cancer vaccines that can stimulate the immune system to fight more effectively and eliminate cancer even before it emerges. I think emerging areas that are extremely important, there are several, of course. Our current understanding of cancer only teaches us the things we don't know well enough or don't do well enough. I think two that I would draw attention to are understanding really the complexities of cancer, which the more we learn, including at the genetic level, the more we realize just how complex cancer cells are and how much heterogeneity exists within a tumor. We think about cancer genes and the alterations in cancer genes. We now know that there's probably 10, 20, 30, 50 different alterations within an individual cancer. And each of these are contributing in some fashion to the biology of the cancer cell. But we're actually quite limited in our understanding of how these different mutations and the pathways that they control interact. And for this, we need systems biology, integrated methods that require mathematical and computational modeling, network analysis, to really appreciate the degree of complexity, how to understand it, and ultimately how to control it. And I think we at MIT are very well equipped to do that for cancer. A second area is imaging technologies. We have good imaging technologies today. We use them clinically all the time, MRI imaging, CT imaging. These teach us that there are masses in a tissue, abnormal collections of cells, but they don't teach us about the biology of those cells. They simply say that they're there, and they're often misleading. For example, today a common problem is overdiagnosis. Mammography is a good example. Individuals have a mammogram, a mass is detected. All of a sudden, there's tremendous need for follow-up to figure out the state of that mass. Is it dangerous? Or might it not be? Might it simply be indolent and never cause problems for the patient? So there's overdiagnosis, overtreatment, and a lot of morbidity associated with that. We need new imaging technologies that not only detect the presence of a mass, presence of an abnormal collection of cells, but what is the biology of those cells? Are those cells dangerous or not? And if dangerous, in what way? And what kind of therapies can be designed to specifically affect those cells?